So we've defined what thermal circuits are, and we've been able to understand how we can take a physical representation of a system and then convert it into a thermal circuit representation, which then allows us to figure out things about the heat transfer rates and the temperature differences across different parts of the system. And so to try to build up the intuition that we would naturally eventually have when constructing, these kinds of representations, I thought that we'd take a look at a somewhat straightforward example of, converting a physical representation of a system into a thermal circuit one. So this is the exercise that we're going to do today. The idea is that you have these two kind of slabs of material, one laying on top of the other with this tiny little insulating strip between them, such that heat transfer does not occur top to bottom, okay? Heat transfer only occurs left to right. In addition, we have that these two things are then both connected to this other slab that's made up of some other material potentially, which is then connected or exposed to, air, right? And each of these slabs and the air itself has some particular material property, right? So each of these will have a thermal conductivity, and the air has a heat transfer coefficient. And, these thermal conductivities could all be different. And then we can see that each of these little slabs also has a distinct cross-sectional area, right? So from the way that this is constructed, the area A3 has to be the sum of the area A1 and A2, but these two areas could be anything that satisfies that criteria, okay? We are also going to assume that the temperature everywhere here on this left side of both of the walls is some temperature T1. Same on the right-hand side. So even though these are different materials, we assume that the temperature on the right-hand side of these slabs is T2. And then we also assume that this temperature is T3 and that the air has some temperature, T air. And remember, like we said before, the temperature of the side of this wall that's exposed to air is not the same as the temperature or the characteristic temperature of the air. If those two things were the same, then no heat transfer would take place, all right, between the slab, right, the edge of the slab and the air. We also have these characteristic thicknesses for each of these two little sections. And so now we can start asking ourselves some questions. If we know what these variables are, or at least if we know some of them, we can ask things like, well, what is the temperature here and here if we know the temperature of the air and the temperature on the left-hand side? Like, how do we find it? How do we find it easily? Okay. We can also ask ourselves, what is the heat transfer rate through the system? Can we figure it out if we only know these two temperatures? We can also ask ourselves, what is the heat transfer rate through each of these little sections, right? Through object 1 and 2. Like, we know that the heat transfer rate has to split up. How does it split up? Can we calculate it? So that's what we're going to be doing today. So let's try to figure that out. Well, the first thing to note, the first thing that we have to do is we have to check whether or not the assumptions that we would normally use to analyze a system with thermal circuits are valid. All right, and I'll remind you that there's 4 key assumptions that we always have to make in order for us to be able to take a physical system and analyze it in the context of thermal circuits. So, first step, is everything in this setup steady state? Well, it doesn't look like we have any temperatures or material properties that vary over time. At least we're not told so explicitly. So it makes sense to try to assume steady state. And then if we get nonsense answers, then we might say, oh, maybe the system isn't actually in steady state. Okay? But we can just assume that for now. Nothing is going to change over time. The material properties appear to be constants because, they're just singular numbers. We're not giving a function of these things over space or over temperature or whatever. So, second assumption down, none of these elements have been declared to have a Q dot, right? None of these are generating thermal energy. So because there's no volumetric thermal energy generation, that assumption is satisfied too. And the final assumption that we have to make is to assume that heat transfer is happening only in one direction. And this is one that we kind of really roughly have to assume, hinging on the fact that there's insulation here, right? That there's a strip of insulation that prevents heat transfer from occurring this way. And why do we need to kind of assume that there's a strip of insulation? It's because remember that because these materials are different, you might expect there to be a temperature balance in this direction, but in the absence of the insulation, there might also be a temperature imbalance in this direction or this direction, right? And so if that is the case, we wouldn't be able to make the assumption, so we just kind of have to rely on the insulating strip and say, okay, you know, heat transfer is only happening in one dimension, which is left to right or right to left. Okay, so we define a little x direction over here, and then we just say that heat transfer is only happening in the x direction. And in case it's not obvious from the diagram, this is a planar system. These are just walls, like planar walls. So we don't have to worry about cylindrical coordinates or anything like that. Okay, so how do we convert this representation of a system into a thermal circuit? Well, it's actually, in my opinion, a little bit easier to work backwards. All right, all that we have to do is identify the different pieces of the element of the system that are resistances. Okay, so, you know, is this a resistance? Is this a resistance? Is this and this a resistance? What do those resistances mean? Like, what are their values? How do you calculate them? I'm going to start right to left, a little confusingly, just because of the fact that it'll be easier, right? And so the first thing is, I've numbered each of these distinct elements in my system for ease of representation. So I'm going to write a thermal resistance, I'm going to give it a value, and then I'm going to pretend like I already know it and can just keep writing those resistances without having to refer to the explicit expressions. So what is the expression for the resistance associated with this material, which is air, right? Well, the air here and its connection to the wall, heat transfer there is happening through that connection via convection, all right? And as a result, we can replace the air element with a thermal resistance, which I'm going to say is R4, and which is equal to the expression for a convective thermal resistance. Now, that expression was 1 over HA. That's the general expression for a convective thermal resistance. But what is this A? A is just the surface area over which the heat transfer is taking place, right? Which the convective heat transfer is taking place. And if you'll notice, right, if this is a planar wall, this rectangular, then this area A3, right, that cross-sectional area is constant everywhere. So of course it has to also be the area of this surface. And so this area is A3. So what are the temperatures on either side of this convective element? Well, from the perspective of convection, it's helpful to imagine that this characteristic temperature is kind of the temperature of the air, like far away when it's not being perturbed by the weird thermality of this composite wall. And so this temperature over here on the right should be T air. The temperature on the left-hand side is the temperature of the left-hand side of the air, so to speak, which is the temperature of the right-hand side of the wall that's touching it, okay? And so we would write this down as T3. And so this tells us, this is the representation for a convective, thermal resistance. And this is how you kind of get its values. Over here, right, now we have a solid object. Now we usually model this via conduction, right? And so we use a conductive thermal resistance, a planar conductive thermal resistance. So we take this wall and we create a thermal resistance. Now, we already know the temperature on the right-hand side of that wall. The temperature on the left-hand side is just T2. right, by definition. And then we say that this is R3, and which has a resistance, which is just the planar conductive resistance of this wall. And so what was the expression for that? Well, it's just L over Ka. Right? That's the general expression. It's the thickness divided by the thermal conductivity times the cross-sectional surface area. So what are these values for this wall? Well, the thickness is Lb. The K is K3, and the A is A3. All right, so that's our expression for the thermal resistance and for the characteristics of that chunk of the thermal network, of the thermal circuit. Okay? Now we have to deal with these two, okay? And this one's interesting because it's a parallel circuit, right? Like, it seems like whatever the heat transfer rate in this system would be, it splits up into two different, channels, and then eventually recombines over here. All right, so because it's recombining, we know that whatever this parallel setup has to be, it eventually has to combine right here into the singular node. So what are we going to do? Well, let's see how much space I have to draw this. So what's happening is that I have two parallel thermal resistances. Because these are brick walls, right? Or walls made out of whatever, both of these have planar conductive thermal resistance. All right, so we would say that this is R2. We would say that this is R1. And then this temperature over here is just T1. And so this is the thermal circuit representation. Now, what is R1? So I'm just going to write R1 over here. It has the exact same form as this, right? So we're dealing with the individual thermal resistances, so there's no weird math about adding up inverses or anything like that. This is just wall, and so therefore, it has a thermal resistance of LA over K1 A1. So this is R1. R2, in the same vein, is LA, right? Because they share the same length, right? The same thickness. They both have the same thickness, but they do not have the same thermal conductivity or the same cross-sectional surface area. Right? So R1, R2, R3, and R4. These are our expressions for each of the thermal resistances inside of this thermal circuit, inside of this thermal network. And now the question is, okay, assuming that we know all of these things, assuming that we know what T1 and T air are, can we figure out what T2 and T3 are? Can we figure out what the heat transfer rate through this thermal circuit is? And the answer is yes, but we have to start to create equations and solve them. And so now that we've created this thermal network, it actually doesn't matter. Like this representation that we had above can be fully replaced with the diagram that we drew below. Now, what is the general process for solving thermal circuit problems? The general process is just to say that as long as we are dealing with a system where all of the assumptions of thermal circuits are satisfied, we are going to get that Q times R is equal to delta T. And the idea here is to say that this resistance, this thermal resistance that I'm defining, is the equivalent thermal resistance. So if I take any piece of this thermal circuit and I want to try to analyze what the heat transfer rate through that chunk of the thermal circuit is and relate it to the temperature difference between either ends of that chunk of circuit, it's going to be linearly related via some equivalent thermal resistance that we would have to calculate based on the rules of like, how do we convert, how do we add up series thermal resistances? How do we add up or convert parallel thermal resistances? So how do we do it? Well, we want to go from here to here, right? So we want to figure out this delta T, okay? We're going to assume that there's some Q that's moving left to right. We're just making that assumption. If it comes out negative, then we know it's moving, right to left. And we want to figure out the Q. And we have to do that by calculating the equivalent thermal resistance of this entire thermal circuit, right? And this process happens via summation. So we have these expressions for R1, R2, R3, and R4. I'm not going to write down the whole things in the coming sections. I'm just going to say like R1 and R2 and R3. Okay, so I'm going to keep it expressed in terms of that. So let's take a look at this little chunk of thermal circuit over here. Okay, so these two are just two thermal resistances in series, right? They're connected front to back. And it doesn't matter that this is a convective thermal resistance or that this is a conductive thermal resistance, because in thermal circuits, who cares, right? The only thing that affects is what the actual value of those resistances is. So what we can do is to try to do the replacement process that we had talked about previously, where we just replace these two with a thermal resistance that, because these two are in series, has the thermal resistance of the sum of both of them. So now we can replace this entire piece of the thermal circuit with an equivalent thermal resistance that goes from T2 to T-air, right? So we're skipping T3, and which has a thermal resistance that is R3 plus R4, because again, we've added up, the thermal resistances to get this equivalent expression. So we did that over here. Now we have to figure out what to do over here. Okay, well, I can't just add this to this because, these are not quite in series, right? Or at least I have two resistors that are connected to the back of this one. So how do I fix it? Well, I have to find the equivalent thermal resistance of these two and then go and add them up. Okay, so what are the rules? Well, once again, the idea is that this equation still applies. It's just that the formula for the equivalent thermal resistance is different. And when you have parallel thermal resistances, I'll remind you that the inverse of the resistances add. So that is to say, for parallel elements, 1 over the equivalent thermal resistance of this thing is equal to 1 over R1 plus 1 over R2. Right? This is what we mean when we say that the inverse is add. And so what we can do now is to say, well, if this is the case, then the equivalent thermal resistance is just equal to this thing inverted, right? And so, as long as you know what R1 and R2 are, this is a relatively simple expression. And so all we do over here is we replace the two parallel thermal resistances that we had before with a single thermal resistance that now is equal to 1 over R1 plus 1 over R2 inverted. Okay? So this is what we're left with. And then, of course, now these two things are in series. So now all I have to do is just to add this up. Okay? And I can add them up. To eventually obtain what I was looking for, which is a thermal circuit consisting of single thermal resistance, where the left-hand side is T1 the right-hand side is T air, and then this thermal resistance is the sum of these two. So 1 over R1 plus 1 over R2 inverted plus R3 plus R4. So we add these up in series and then voila, we have this. And the reason that this is useful is because now we can determine what Q is pretty quickly, right? Because my delta T, if we assume that Q is moving, left to right, delta T is just T1 minus T air, right? We're trying to keep this delta T positive whenever the Q is actually going in the direction we think it is. And so if we know these two values, we can immediately say, well, Q is just equal to T1 minus T air divided by the complicated equivalent thermal resistance that I had found previously. And so we can then immediately obtain the following expression. So this is great. This is wonderful. Okay. Now that we know what the Q is, now that we've been able to figure out an expression for it using only T1 and T air, then now we can ask ourselves, well, what is T2? What is T3? And the answer to this, now that we have the Q, is actually somewhat straightforward. So I'm going to remove this value. I'm going to assume that we've written it down in a notebook or something like that, or that we can confirm that we know it. And so all I'm going to do is just use this expression. I'm going to write down Q, not with this whole thing, but just say, oh, well, this is what Q is. So what we can do now is to say, well, let's see, the original thermal circuit looked something like this. I'm going to save myself the time and not write down absolutely everything about it. But the original thermal circuit looks something like this, right? We had the two parallel chunks of wall and then another chunk of wall and then air, right? And we wanted to figure out what T2 or T3 were. We knew T1 and we knew T air and we knew the resistances. So how do we find, for example, like let's say T3? Can we find T3? The answer is yes, as long as we know the Q. Because we can use this law on any chunk of this thermal circuit, including just this little resistance over here. So in this situation, right? So this thermal resistance, which we had labeled R4 before, right? It's just 1 over H times A3. So this thermal resistance over here that represents the air can be analyzed from the perspective of just saying, well, Q times R4 is equal to the difference in temperatures between here and here. Now we had assumed, right, that there was a Q that was going left to right. That shouldn't be changing as we hit this little branch. So we also expect there to be a left to right Q, the same Q, because, heat transfer rates in the system are conserved, at least after they, split up and then come back, right? So Q times R4 is equal to the temperature difference, T3 minus T air. And we figured out what the Q was before, right? We knew what the R4 was from the start. We know what the temperature of the air is from the start, but now we can find T3, which is unsurprisingly just T air plus QR4. All right, so now we have another temperature. Can we find T2 using the same method? Yes. All we would have to do now, although technically we have options, we could either do the thermal analysis from here to here, right? And then say, oh, well, the equivalent thermal resistance we use is just the sum of the convective and the conductive resistances we found before, so we could do that. Or we could also say, well, let's try to just do it over this chunk knowing that we already have T3. right? So let's just take a look over here. And then we had said that this thermal resistance was R3. This was a conductive thermal resistance. And so we would say that Q times R3 is equal to T2 minus T3. We already know the Q. We just found the T3, so the only unknown is the T2. And then you can use this process, no matter how long this little daisy chain of resistors is, to be able to figure out what the temperatures are using this formulation. So this is one of the things that makes working with thermal circuits so much easier, which is that you don't have to analyze each individual piece. You can always just work with the parts that will give you the information you need, assuming that you have all the other information you need, and then you can work on filling in the gaps however you want. Okay, we could have always just said, well, who cares about T3, right? Just add both of these up, and then the delta T is T2 minus T air, and then we would have been able to get something that worked too. All right? So now, right, the remaining question here is, we know that the Q has to split, right? We know that this has to split into two chunks. And now we have to try to figure out, well, what is Q1 and what is Q2? Like, how can we calculate those? Once again, this thermal circuit law is going to save our butts. And the way that it's going to save our butts is because, okay, we can do this thermal circuit analysis over each individual little resistor in this parallel connection. And what would that look like? Well, for the top one, we can just say this is Q1 times R1. And then this is equal to a temperature difference. The temperature difference is at the end, right? And for this parallel chunk, it's going to be T1 minus T2. Okay? So T1 minus T2. And so this expression works. Like, we can still do this, even though this resistor is in a parallel connection with another one. And we can do, in fact, the exact same thing for Q2. Where, of course, the delta T is the same for both of them. So does that mean that the Q going through them is the same? No, because remember that these resistances are potentially different. And so what happens is that once you figure out T2, which we already did from analyzing this problem, we can just use this equation on each individual chunk of the parallel part of the original circuit and use the thermal resistances of each portion and that temperature difference that we spent a bunch of time trying to find in order to determine what the Q1 and the Q2s are. Okay? And so even though the temperature differences are the same, the Qs going through them are going to be different because the thermal resistances are potentially different. All right? And so this is a relatively simple example of how we can go through the process of using those expressions for thermal circuits and how we can convert a physical system into its thermal circuit analog by using what hopefully you'll find are a set of straightforward analytical tools. All right? And so this works out perfectly fine. And so we will see how systems like these become more complex, for example, if we add like stranger geometry, but there isn't really that much more to it when it comes to analyzing like basic thermal circuits, right? The only thing that can show up are just maybe more resistances in parallel or more resistances in series, all right? But once you get the representation down, it's just using this equation over and over to get an answer. So we'll take a look at how we can address a system that has cylindrical geometry. It's not going to be very different, spoiler, surprise. But we also should take a look at what happens when some of the assumptions that we use for thermal circuitry don't work on every part of the system. But we'll take a look at that in the next lecture.